Folks, thank you for staying for this next section. It's an exciting session following the keynote. It's a second session on wearables and mobile IUIs. And we have 4 talks in the session. So by the way, I'm Sri Subramanian. I'm a professor at the University of Sussex in human-computer interaction. So today's first talk is going to be on enhancing audience engagement using brain-computer interfaces. And it's going to be given by Shao Yan.
Shao Yan, yeah, thank you. So in our research, we create and design a novel brain-computer interface combined with performing art. And we use the EEG headset to monitor the audience engagement value and also connect it with a virtual environment. The virtual environment will create a content-related performing cues to increase the audience engagement. And in general, our work was trying to help the stage designer to improve the design of live performance from the audience perspective. If we think of a complete live performing as an iceberg model, that we could see above the waterline is what the audience could see, the performance content. And this part is totally visual, and it determines that whether a performance is great or not. And also for a live performance, it also described as the communication between the actor's action and the audience reaction. So this part is under the water. And a lot of research, they start to use explicit measurement to measure the quality of performing art since 1990s. And after decades, some of the research, they are measuring the audience biometric data when the audience are watching a performance. If we look at some of the related work, we could see that most of the work, they are require the passive and active behavior from the audience. This kind of called stimulus and response interpretation that could help the researchers to understand the audience, but somehow it also disturbs the audience when they are watching the performance. And also most the research, they were just measuring the audience with no feedback on the performance itself. So from this, our research work was intended to not only measuring the audience response, but also we create content-related performing cues to increase their engagement levels. And let me talk about the digital performance. The digital performance implies digital technology to reconstruct and to achieve the performing arts events, including 3D modeling of the theater structures, animated sceneries. And this is one of the virtual theater that we are designing in the experiment study. Here, we are using the laser scanner to measure the complex structure. And also, we create this virtual environment in a game engine. And we provide this environment to the stage director so they can create, manipulate, and test all the performing elements in a totally interactive way. And also for the performance, the motion capture technology was offering a different approach for performance simulation. So we could obtain the performance dance movement and even their facial expression. And also we can map all this data onto a computer-generated model. So in one of our performance, we invited 2 professional dancers, and we record their skeleton information and opt into a 3D model to complete the performance. And also we need to centralize the multiplayer's motion at the same time. We can look at the concept figure. So the virtual environment, that works as an adaptive interface to create different performing cues according to the audience engagement state. The engagement state was generated from the EEG signal. And here, the EEG signal was sensitive to the user's cognitive state. And compare with other measurements for the audience emotion, the EEG device, they are more suitable for a theater setting. It could help the users to focus and immerse in the theater experience. And also the EEG-based engagement formula has been using widely to estimate the audience task engagement in the HCI field. And here we averaging 2 pairs of the electrodes because they are mainly related to the user visual attention. And also we use basic ICA algorithm to remove the EMG artifacts. So our system consists 3 levels: interface level, logic level, and the engine level. We capture the EEG signal from the emotive headset and generate the audience engagement. And also we use a detection algorithm to determine what time we should create the performing cues. And the final virtual theater was created by a game engine, and it will be presented at the 3D projected screen. We integrate an algorithm into the proposed system, so we can determine what is the right time to imply the performing cues. And here we generate 2 different values from the original engagement level, a smooth engagement value and an averaged engagement value. And also we set two different thresholds. The thresholds could separate an individual audience into 3 different status: positive arousal, stable engagement, and less interest. So when the condition meets the decreasing case, that a drop point will be marked and a performing cues will be triggered and displayed at the same time. When the condition meets the re-engaging case, that we are considered that the audience engagement has been regained successfully. We designed the performing cues based on the theater performance theory, and it includes the stage machinery and the performance. Stage machinery usually contains scenic design, lighting effects, sound effects, and special effects. For each one of the unit, we give some basic performing cues. And here is a crucial question, is that usually for a live performance, it has a narrative structure with a setup, a build, and a climax. So we want to help the audience to build up their emotions. And here we're working with the stage director to create content-related performing cues. We are not buying to create by categories, but by degrees. We divided each performance into different paces, and in each pace, we create pairs of single and multiple performing cues. In usual, the multiple performing cues has more impressive effects than the single performing cues. And we took 2 different performance in the experiment. So for each experiment, we have 3 different scenarios. There are no performing cues, single performing cues, and multiple performing cues. After we helped the audience to put on the EEG device and the 3D glasses, we will leave a 20-second collaboration time. And during this time, the audience could get used to the system, and also we can get their baseline to establish the decreasing threshold. And in the formal testing period, the single or multiple cues that could be triggered However, if it won't success, that we will continue to trick the next performing cues after a 15-second interval. And in the evaluation, we use one-way ANOVA and Likert scale measurement to analyze the objective and subjective data. So the first performance is we choose a 5-minute scenes from opera Siegfried, and finger A is the real theater performance. Finger B is the simulated performing, and finger C and D are a single performing cues which the light was changing its color, and a multiple performing cues that combines the actor's movement and some special effects. We also choose 3 different participants in each one of the scenario. So for no performing cues, that the audience engagement level was gradually decreased, and after a significant drop point at a time about 1 minute and 20 seconds. And also from the result, we can see that compare the time of the study of positive arousal and less interest, the audience actually they get more engagement from the multiple performing cues compared with the single performing cues. And for the second performance, the Tramp of Horses is a modern dance, and the results shows a little difference compared with the opera performance. By applying the performing cues, the audience they get more engagement compared with the no performing cues. However, from the selected engagement values, we could not see a clearly difference between the single performing cues and the multiple performing cues conditions. And we think this is maybe because that for modern dance, it usually has a really fast-paced rhythm, and for the decreasing threshold, it could happen randomly. So here's our conclusion, that our system could successfully measure the audience engagement, and by using our algorithm, we could detect the audience engagement that whether it was decreasing or re-engaging. And second, the performing cues that we create could increase the audience engagement in real time. However, for the different kinds of the performance, single and multiple performing cues, they may have different impacts, and especially for a narrative structure performance, the multiple cues they works better. So for the future work, because right now our system is user dependent, so we are thinking, is it possible that we could measuring the crowds, and also is it possible that we could generate a model that could suit for most of the audience, maybe in one specific performance. And this is some of the research we'll do it later. And thank you.
So we have time for 1 or 2 questions, if anybody wants. So let me start with one question.
Yeah.
In your experiments, you only had 1 participant at a time. You had 1 user.
One user, yes.
And did you find differences in moments when they were engaged and between users? Did you find any differences?
Yes. As I was saying before, that because we conduct 2 different kinds of the performance. Yeah. Okay. So for a narrative structure performance like the opera, that we found that most of people, they have some certain times during their watching the performance, they are decreasing. But however, compared it with the modern dance performance, it not see clearly the similarity. The people shows very different.
Okay, and so how do you have any ideas for how you will then use this when you have many people?
For many people.
Yeah, so you say one of your future works is crowd measures.
So actually, it's in a very early stage, and we are thinking about maybe we can choose a longer opera performance, maybe like 10 to 15 minutes, and we can to let users to test that. But first, it's also one by one. But we can generate some certain time point that was decreasing, so we can redesign the performance and we can do the experiment again and to try to compare it with the first time if all the users get better engagement.
And have you had any feedback from the theater producers or
Producers,
yeah?
actually they are not, they're just concentrate on the art part. So when they're like, because they're working with me, so they're kind of inspired by the audience response. Yes.
Okay, thank you. Thank you.
Yeah, thank you.
Any question? Oh, okay, thank you so much.
Thank you.
So the next talk is on facial expression recognition in daily life by embedded photoreflective sensors on smart eyewear. And the speaker is
Yes, Katsutoshi.
Katsutoshi Masai.
Yeah. So hi, I'm Masai from Keio University, Japan. So in this research, we address the question, how can we recognize our facial expression in daily life? And let me start by an example. So when I was talking with my parents about my future, and 20 minutes later, I was suddenly asked if I was angry. I was just thinking how, but I may have shown a bad face and bad impression to them, as the talk and feedback was not so meaningful. But I think if I could realize my facial expression at early stage, we could have communicated in a better way. This is one of the reasons why I wanted to make the device that can recognize our own facial expression. And recognizing the state of the facial expression in daily life will help us better understand our affective states. And also, it can show us how we give impression to others and how to communicate in a better way. However, we are not usually aware of the facial expressions in daily life, and only few of us try to detect them. And here I show the early prototype. So we designed a form of eyewear to predict the real-time facial expression. So our contribution is that we developed a device that can recognize 8 facial expressions defined as a universal, and we made a device as a form of eyewear so that it can be acceptable to public. And we analyzed by using our system for a long time the distribution of facial expression. And our smart eyewear is potentially used for various scenarios. First one is the happiness map. So by combining the information of facial expression and location and demographic information, the people can search for their happiest place to live or work by looking at the map. And the second is the care system for elderly people. So our system can provide the overview of their situation. And since more and more elderly people live away from their children, our system may help make strong connections between them by notifying their affective state and provide the appropriate timing to call and talk. And finally, our device can be used for mental management. And a depressed person usually talks little with others and don't show any facial expression. And if a system successfully can detect these situations user in, our might help user and doctors deal better with it. So facial expression recognition is mainly developed by researchers in computer vision field, but using in the daily life, there's a problem like tracking because of the occlusion and the limited view of field. Also, there's a problem of social acceptance, and there's a trade-off between the real-time prediction and the comfortability of wearing if we design as a form of wearable. But there are other ways to recognize facial expressions without using camera. The Light 3 uses the contact-based sensors. like piezoelectric sensors and strain gauge. However, the contact-based sensors can be sensitive to losing the physical contact, and the comfort of wearing can be an issue. And Light 2 uses the photoelectric sensors, and photoelectric sensors can measure the facial movement in an obstructive way. However, this work uses only limited number of sensors, so they can just recognize the specific expressions. So we use the number of photoelectric sensors to detect the various facial expressions. So the characteristics of our smart eyewear can be described with 3 keywords: skin deformation, and many photoelectric sensors, and machine learning. And there are 4 advantages of using our system. First one is an adaptive, more robust recognition comparing to related work. And second one is unobstructive measurement. And third one is simple. So sensor data is low dimensional, so the energy consumption and the processing cost is low, so which is good for the real-time prediction. And the last one is the smart appearance. The sensor can be integrated into everyday glasses because of its small size. So they can use, the user can use in various scenarios. So approach to recognize facial expressions. So we leverage skin deformation caused by the movement of facial muscles, and 17 photoelectric sensors measure the distances between the various spots on eyewear frame and the skin surface on face. And we use IR reflective sensors, which consists of IR LED and a phototransistor. So in the closer distance, the sensor shows a high resolution, like 0.2 millimeter. So it's like a proximity sensor. Now I'll talk about the implementation detail. So our prototype includes the 70 photoelectric sensors, a multiplexer, a transistor, Arduino Fuse, and a repo battery, and XP. And the front frame is 3D printed, and the template is reused from the commercial one. And we apply the band to stabilize the position of the eyewear. And the transistor is used to modulate LED so that in order to reduce the influence of ambient light. And sampling rate is around 80 Hz, and the XP enables the wireless serial communication. Now I show the flow of data processing. So first, user needs to calibrate and record the training data, and and then from the device, each sensor input is smoothed out by applying the low-pass filter, moving average, and then it is normalized 0 to 1, and it is applied to support vector machine to classify the 8 facial expressions. And in this case, the user is smiling, so it recognizes as a happy. And in addition to the trained data, the calculated value CV from the 2 different sensors used for SVM, we considered lower power sensors and the sensors with vertical relationship. And also, we use the 33 dimensions for support vector machine. And this figure shows the visualization of our system. The emoticon shows the result of classification, and the bar graph shows the raw data, and the yellow circle shows the position of the sensor, and the size of it. The size is corresponding to the normalized value. And we evaluated our system, and we asked 8 users to participate in first evaluation, and they were asked to have a shield and mimic the facial expressions made by a maker male. We collected data of 8 facial expressions in different poses, and in one recording of each facial expression, 10 pieces of data were collected, and overall, the 1,200 pieces of data were collected from each user. And there are snapshots from the experiment, so all recordings are performed indoors. And by using this data set, first we evaluated the accuracy of each user's performance with user-dependent training. And for each data set, one recording, 10 pieces of data were divided with the former half as a training set and the latter half as a test set. And the data was applied to SVM, and the result was 92.8% accuracy. So by running the data of facial expression, facial direction, so our device can classify correctly regardless of the direction. And also, we also confirmed that the noise of real wearing cannot be an issue by learning the data of that condition. Second, we evaluated the user dependency. So we trained each user's training set and tested with all other users tested. The scores are quite low, like accuracy is at most 48.0%. So this result suggests that with the current system, we need to, each user require to individual training. However, happy expressions can be relatively recognized with high accuracy, like 71.9%. And as this is user dependent, I'm just showing the example of the each sensor value of the each facial expression. So it's a bit difficult to see, but the sensor data is different depending on each state. And we also tested on different conditions. We collect data from 3 of the participants on different days, only when they look straight. And for each day, we collected 240 pieces of data. And we used the 2 days as a training set and the other day as a test set. And we had 3 participants and average 78.1%. And we also tested during the working. So we use tested as a collect the data while the users are working and making the facial expression. And we have the whole participants and average was 73.1%. And we have demonstrated a C-graph imaging technology last year. And what we found here is that the eyewear, the shape of and the size of the eyewear should be personalized for each user, because sometimes the device slipped out of place and sometimes the sensor data saturated. And we also observed that our device seems to work better for Caucasian compared to Asian people, as they tend to have more expressive faces. And we also did initial field trials in daily life, and we recorded the 90 minutes, like go game, dog playing with dog, and sitcom, and programming. And as you can see, that the distribution of facial expression varied on the activities. And the user showed many facial expressions with dog while playing with dog and playing the game with the friends. On the other hand, the user showed the fewer during the Go game with the computer. It seemed that social interaction caused more facial expressions, and in other words, facial expression plays an important role during the communication. And we compared the activities between watching the sitcom and watching the crime drama. So they showed the different expression, so these information can be used for the content creators. So discussion, we confirmed that our device needs user-dependent training, but I think it is okay because I realize a personalized item and it can be used for a long time by one user. And however, we believe external data sets help to reduce the cost of learning phase and improve accuracy of recognition. And in multiple days in working situations, accuracy was reduced because the position of the device and lighting condition changed. And another factor to reduce accuracy was the difficulty of making same emotions because they show slightly different expressions, but it is natural in daily life. The limitation, so we only assume that facial expression caused skin deformation. However, physiological behavior like yawning and rubbing one's eyes and resting one's cheek in one's hand, and moreover, talking can cause skin deformation, and those can be a noise. And our system cannot recognize the every mouth movements because we just place the sensors around our eyes. So for the future work, we like to capture natural facial expression. Natural facial expression includes complex or subtle expressions. And in field trials, angry expressions were observed during the programming. However, it can be related to mental effort, confusion, or frustration. And in order to understand user deeply, so those information can be important. And second, we want to improve the accuracy in various scenes. So first, as I said before, the IUI should be personalized for each user. And as the photorefill sensors is based on the infrared, so in the environments where the IR LED is, there are a lot of IR LED, the sensor cannot be worked. So we need to apply the optical filter to reduce the influence. So conclusion, we propose a novel smart eyewear that recognizes the wearer's facial expression in an unobstructed way by applying machine learning to the data from many photorefill sensors. And we implemented our system with the form of the eyewear so that it can be acceptable to public. And with the eyewear device, we showed that we can get the insight of users' affective state by recording facial expression for a long time. Thank you.
Very nice work. I love the form factor you built. Question about the field trial when people were either playing with the dogs or watching Friends or doing the programming. How did you find out the ground truth of these videos? Did somebody else go through frame by frame and label it?
So it's just initial field trial. Yeah, that's a good point. So we wanted to record the videos, but we just recorded the data, and we rely on the data based on our evaluation results. So we don't have ground truth.
Hi, thank you. This was actually fascinating. I have two questions. One is the precision levels that you reported, were they achieved using the same classifier across different individuals, or was it the same classifier like used universally across different people?
So all user needs to record their own data. So it's
their
not
own model for
Yes,
classification. So this was within subject kind of analysis.
Yes.
Okay. And then my second question, had I wanted myself to experiment with your device?
1 second, please.
If we want to use your device, can we? Is there any way we can achieve? We can access it? Do you sell it?
Maybe in the future.
Not now. Okay. Thank you.
Hello, I'm Prajwal from Arizona State. This is really great work. I was wondering how you do the, where you store the data while you're doing the sessions, and how do you transfer the data?
So okay. So data is collected by putting the label, by just putting the button. So while users making the facial expression, the intentional facial expression, then the observer put the label for
I meant like the medium of data collection. Like, is it Bluetooth, or does it like store somewhere on the sensor and you collect it later?
in the laptop, so CSV file.
Okay. I mean the medium of transfer. Is it like a wired or?
It's
is it
a
Bluetooth?
Zigbee, so serial communication.
Okay. And you're doing the processing afterwards, right? So it's not. Is the expression analysis happening in real time, or you take a chunk of data and then classify it later?
It can be predicted in real time.
In real time. Okay. Yeah. Thank you.
Thank you.
So while the next speaker sets up, this is a short talk towards using mobile head-worn displays in cultural heritage. It's going to be given by Natalia Weinstein.
Weinstein, right. Second. I'm studying in the University of Haifa in the Department of Information Systems, and I'm going to present you my first part of thesis work. My advisors are Tzvi Kuflik and Joel Lanier, and this is a research about head-worn display in museums. So, the wearable technologies can enrich our lives in different aspects. One of these aspects is a museum visit. Utilization of head-worn displays in the museums allows us to provide to the user a wearable augmented reality display without the necessity to hold the device or to look at it, and without distracting the user from the real object. So we can see here example of art exhibition where the user can see art exhibition without explanation and augmentation, text augmentation of the art exhibition. This study focuses on exploring the potential of head-worn display to enhance the museum visit experience. The user is the center of the research, so we want to understand the user requirements, to understand what are the needs of the users and what are the preferences of the users. From these requirements, we are going to derive the design of the system and implementation of the head-worn display museum guide. The guide will be evaluated in the real museum with the real visitors. So, to find these requirements, we did study with 17 participants. We did interviews with them. The ages are from 90 to 57, and the visitor visited at least once the museum. Before each interview, we gave to the participants Vuzix M100. Vuzix M100, this is a head-worn display, similar to Google Glass. We can see two examples, two pictures of these glasses. So each participant wore it and experimented with the glasses to understand the potential of such device in the museum. After that, we conducted interviews, semi-structured interviews. Each interviews were recorded, and we wrote all the interviews and analyzed the data to find the group of the requirements. So, the requirements that we found, system proactiveness. In this aspect, there are questions whether the system should keep the user in control and provide information just in accordance to the user request, or the system should take initiative and provide by itself the information. So most of the users prefer to keep the user in control, where the user decides when to receive information. About interaction with the device, with the head-worn display device. There are many options to interact with the device. Most of the users prefer to interact with additional mobile device, like smartphone. Some of the users prefer to interact with buttons and with slide gestures near the device, with voice commands and mid-air gestures. What is interesting that some of the users objected to voice commands, mostly because of the quiet environment of the museum and the request for privacy. Device characteristics. User asked for lightweight device, the ability to adjust and remove the display. Some of the users prefer the display for both eyes located at the center of the glasses. Information delivery. There are several forms that the user prefer to have, and combinations of these forms, like text, some story, audio to listen to the story, video, some video, some movie, images, and information in the real world position, like augmented reality. Personalization and privacy. Users would like to have the opportunity to choose the information from multiple content items. In addition, users would like to have personalization to receive personalized data, Some of the users agreed to be monitored during the visit, and even agreed to data collection from external sources like Facebook and Twitter. Some of the users asked to be in control of data collection, to have the opportunity to turn on and turn off the data collection of the device. Additional features: navigation in the museum, which can save time to the user. Recommendation for additional museums in the city. Group interaction, when the user comes with friends or family. Additional preferences is the possibility to change the content of the presentation content, like zoom in and zoom out the virtual image and to adjust the audio volume. One of the users asked for training in the beginning of the visit. This is a new device, so training can be useful in this case. In addition to the requirements, we did prototype, which includes the user, which comes to the museum, see some exhibit, want to receive information about this exhibit. Press button on the device to receive some information, but the system should know what's the position of the user. So the Android application of the museum guide takes picture and transfers this picture to the server. The server performs image recognition. In this way, we know the position. And server sends the information about the exhibit to the user, to the guide, and the guide will present it to the user. The future world. In the future, we want to compare the headboard display with more conventional museum guide, the smartphone. We're going to use the same museum guide for both devices, for headboard display and for mobile device, for smartphone. The study will be conducted in the real museum with real users. We're going to evaluate aspects of usability, additional experience, and group interaction in the museum. We're going to collect the data with log files and questionnaires and interviews. Thank you.
Up to the mic. Let me start by asking, you said that you collected participant information on desire for group interaction. Did you get any more data from them on what type of group interaction would be nice, or what do they like to have?
The idea is that when the user comes to the museum, in most cases they don't come alone, so they'd like to have some guide to interact with additional visitors to the museum.
But did it say how, or what would they like to see with the group?
No, they'd like to us to do that work to prepare.
Okay, see. Did you show them a scenario before you interviewed them, or how did they come up with the requirements for images, videos, for zooming in, and so on? How did they know that these are the requirements? I mean, did you just ask them?
First of all, we gave to the users the device, so they could experiment with that and to know what are the features. Some of the user knows about cardboard display. And yes, this is semi-structured interview, but we asked about opinion of the users in some kinds of what would you like to know, to see.
Okay, all right, that's great. No other questions? Thank you so much.
Thank you very much.
Talk of the session is Sweep Sense. and ad hoc configuration sensing using reflected swept frequency ultrasonics. And the speaker is Gerard Laput.
Thanks for the introduction. This project I've done in collaboration with my colleague Anthony Chen and my advisor Chris Harrison, all from CMU. So let's talk about SweepSense. Many existing devices can be made more intelligent if they had the ability to sense their surroundings and physical configuration. But enhanced sensing capabilities could mean adding special purpose sensors, which inherently increase device size, price, and complexity. Yet the phone in your pocket already contains many hardware capabilities designed for very specific features, like music or network connectivity. But if you simply examine most devices, it is clear that one of the least common denominators are speakers and microphones. In fact, speakers and microphones can be found in smartphones, small-scale earpieces, to full-size laptops, and on and on. So the question then is, how can we appropriate speakers and microphones into a sensing mechanism that requires no modification of the hardware or the infrastructure? So in this work, we propose a technique called SweepSense that uses existing speakers to emit inaudible ultrasonic frequency sweeps, and it uses microphones to measure the reflected signal, which changes based on the geometry and properties of nearby surfaces. So let's briefly talk about related work. There's been early research in the HCI domain that utilizes sound for input and interaction. So first are time-of-flight localization techniques that uses pulses or Doppler shifts for localization or device interaction. Second are passive acoustic techniques such as skinput, which rely on user to generate sound like taps on the arm. And lastly, there's work that are active acoustic fingerprinting approaches, which uses detachable piezo sensors or speakers on the finger, which can then be analyzed by a microphone. But again, most of these techniques rely on special purpose hardware, whereas SweepSense takes advantage of devices' existing speakers and microphones. So how does SweepSense work? Let's dig into some details. First, the speaker emits a continuous inaudible frequency sweep. So the question then is, why use a sweep instead of just one frequency tone? So this has a lot to do with robustness, because a sweep allows you to get a full range of the signal instead of just relying on one frequency tone. And if you just only have one frequency tone, that's very susceptible to noise. And for the sake of visualization, the sweep that you're seeing here is a much slower version of the actual sweeps that we are using. So I want you to focus on the graph on the left, which is the frequency response. Notice how the sweep at this speed creates like a wave motion, so it's like, scanning like a wave. But if you speed this up 30 times faster, the wave behavior disappears to a point where the frequency response looks constant. So instead of that wave, it's just constant. This is the behavior that you want, because this way, changes in the frequency spectrum can be interpreted and characterized very easily. As opposed to that wave, you just have something that's stable. And then any changes into that signal you can use to characterize changes in the environment or where the device is, for example. Okay, so once the sweep is transmitted from the speaker, it goes through the air or some environment, and it is then received by the microphone. And this is what the microphone's frequency response looks like when plotted over time. So that is the sweep that was generated earlier, and this is the frequency plot over time. So now let's compare the original sweep versus the one that's received by the microphone. So the one at the top is the original, the stable signal, and the one at the bottom is the signal that is being received by the microphone. Notice how some of the signal's energy has dissipated, and there's a dip somewhere in the 22 kilohertz spot. This change is caused by external surroundings and physical configuration between the speaker and the microphone. So in general, you have a frequency sweep that is generated by the microphone and that emits ultrasound from a specific range, let's say 18 kilohertz to 40 kilohertz. The system then monitors the received output using the microphone, And then depending on the surrounding physical configuration, the return signal will be drastically different from the original signal, for example, because of attenuations. These return signals can then be used to characterize the configuration of the device or the environment. For example, when something is nearby or when something is far away. We then extract features from the return signal, such as raw FFT, stat features, center of mass, etc., and we feed them into a machine learning algorithm for classification or regression. In this case, we use SVM for classification and SMO-reg, a version of SVM, for regression. More details are on the paper. So we build 2 example applications demonstrating the feasibility of our approach. Here, SweepSense emits inaudible sounds through both earbuds. A microphone is located, integrated into the earphone wiring. So when the earbuds are in the ear, the frequencies are attenuated. When it's out, they are dissipated into air. And you could use that to detect which earbud is on or off, and then you could use that to interact and trigger interactive events. For example, answering a phone call when one earbud is removed, or stopping music when both earbuds are out. There's another example where we use a laptop's integrated speaker. Changing the lid angle changes the reflectance behavior of different acoustic frequencies. And then we use this data to train a regression model, which can then act like a lid angle sensor without extra hardware. This could be used, for example, to switch between different interactive modes. For example, tilting the screen can trigger a dashboard. Also, our evaluations show that our model can be within 4 degrees of the correct angle. So like all techniques, our approach has limitations. So I'm going to go through them really quickly. First, ultrasound may be audible to some children and pets. And this is related to the second limitation, which is that most existing hardware has a sampling rate limit of 44 kilohertz. But as hardware improves, we can increase our ultrasonic frequency range beyond human hearing. And finally, the trained models are hardware specific, which means a model trained on a MacBook Pro, for example, may not work on a Dell laptop, although it is possible to use a library of models that can be reused and shared across many users. So in the future, we hope to extend SweepSense to monitor physical configurations in much larger contexts where speakers and microphones are present, such as in cars, conference rooms, grocery aisles, or even public address systems. So much bigger scales, like everywhere there's speakers and microphones. That's all the time I have, and with that, I now open the floor for questions.
So, as a session chair, I can ask the first question.
Sure.
My question is, you have only binary state you determine only between A and B in each condition that you do, right? So either the earbud is on or off, or you close the laptop or turn it on, keep it open. What if you had many more conditions that you want to determine from?
That's a great question. So actually, our system in the earbud example, there's 4 states, actually 5 states.
Okay.
Actually, 4. So both earbuds are in, left is out, right is out, or both are out.
I see.
So in that case, there's 4. In the laptop example, it's actually a regression model. So it's from, let's say, 110 degrees to like 20 degrees, and they're like, states in between. So that there's like so many states you could do there. Because you're using SVM, it's very flexible and can scale across different types of classification. So depending on your application, you can make that fit to not just be binary, it could be like more classes.
All right. Okay.
Mm-hmm.
Hi, James Crowley, Grenoble, France. That's really cool.
Thank you.
I love it. We're going to duplicate that. I was
Thanks.
surprised by one small detail. Maybe you've tested it. I've understand there's a phenomenon that up through adolescence, some people can hear up to about 20 kilohertz, or at least 17, 18. And I was surprised to see you starting at 18. Have you tested this on adolescents younger than 20 years old?
So in our user
In the
studies,
presence of?
that's a great point. So there's been documented behaviors where people can still hear ultrasonic sounds. In our user studies, most of the people were not able to hear them. But we've done other work that uses ultrasound, and you're right, some people can hear it. But again, as hardware improves, where you can cross that 44 kilohertz sampling rate limit, you can just move the range.
There's a commercial
something.
product that chases away adolescence. that people put outside stores.
Oh, okay.
Specifically emits a frequency that only they can hear.
Yeah. Also, there's an app out there where someone emits a ultrasound and they can guess how old you are, just based on that.
What was the frequency of the sweep?
So we were using 18 to.
Oh no, but that's the those are the sampling frequencies. But you were sweeping at some rate.
Okay,
isn't
so so we start from 18 kilohertz
Yeah.
up to
40.
20. We could go up to 40 if the sampling
Yeah.
rate is 96,000, which the laptop does. But for phones, they can only go up to like 23.
All right, so and that is a frequency that you now introduce in your. That's a new frequency that you introduce in your classifier, isn't it?
Yeah, so you go, you just sweep from 18 to 24. You just do that really fast. Yes.
Corey Pittman, Central Florida. So I've actually done a lot of work in this area as well. You said you made a lot of concessions to increase robustness by not using a pure sine tone, instead using a sweep, which is interesting. But I had a question about, you said geometry, so you had to learn a particular recognizer to be able to learn these states. But when the geometry changes in the environment outside of, say, the user's head, so say, with the laptop example, if you had another surface right next to the laptop, did you ever test to see if the recognizer was able to actually correctly classify if there was additional changes to the geometry besides just the lid closing?
That's a great question. So in our user studies, we actually tested, let's say, the laptop configuration across different environments, not just in the lab, but we went to Starbucks and atriums and stuff like that. And what we found is that the biggest contributor to accuracy is how you train your data. So in that case, you would want to train your data so it's exposed to a lot of different environment configurations. Then it can scale robustly across different environments. But you are right, audio is very sensitive. So in order for you to make those good accuracies and be robust, you have to train your model very, very robustly too.
Thank you.
Yep.
All right. So we want to thank the last speaker and thank all the speakers in this session.
Thanks for having me.
So before you break for coffee, I have one small announcement. There's a sign-up sheet at the registration desk for those who are leaving this afternoon and want to share a ride. So please use that facility. Thank you.